Good morning, everyone. For today's discussion, I'm going to discuss to you the Chatellier's principle. But before we dig into our main discussion, let's have our learning objectives first. So, first and foremost, we're going to define the Chatellier's principle. Second, predict the direction if shift for an equilibrium under stress. What is Lee Chatelier's principle? In all systems, whether biological, physical, or chemical, there is a constant desire at the chemical and molecular level to maintain equilibrium. Equilibrium is best defined as a central point of balance, like a leveled weight scale for which the forces within a system are consistent. In every scientific field, there are different concepts that describe states of equilibrium. For example, in biology, homeostasis describes a state of internal balance for living organisms. In physics, static equilibrium describes a state of balance forces of motion on an object, while in chemistry, there is Le Chatelier's principle. This principle is also known as the equilibrium law and used to predict the effect of some changes on a system in chemical equilibrium, such as the change in pressure, temperature, volume, concentration, and the principle is named after the French chemist Henry Louis Le Chatelier. So once an equilibrium is established, the reaction is over, right? But not exactly. An experimenter has some ability to affect the equilibrium. Chemical equilibria can be shifted by changing the conditions that the system experiences. We say that we stress the equilibrium when equilibrium and the reaction starts to move back toward equilibrium in such a way it will decrease the stress. So the formal statement is called Le Chatelier's principle. If an equilibrium is stressed, then the reaction shifts to reduce the stress. Stress and Le Chatelier's principle. If a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium moves to counteract the change. Now, what are those factors that affect the Le Chatelier's principle? So, according to Le Chatelier's principle, there are three factors that can impact the balance of a system at equilibrium. So, these external stressors are temperature, pressure, and concentration. Now, let's begin with the first stress, which is the changing concentration. So, let's consider the hypothetical reaction where gas A turns to gas B, and let's say the reaction is at equilibrium, and suddenly we increase the concentration of reactant A, and according to Le Chatelier's principle, the net reaction is gonna go in the direction that relieves the stress, and since we increase the reaction of concentration A, I mean to increase the concentration of A, the net reaction is gonna go to the right to decrease the concentration of A. So we have here an illustrations where gas A is red and gas B is blue. So since walay color, black sila tanan. And then the equilibrium constant is equal to 3 at 25 degrees Celsius. So let's start by writing the reaction quotient. So QC is equal to B, which is the gas B, and divided by A. So let's calculate the concentration of B and A from our first particular diagram. So B is represented by the blues first, but since walay color, black. Again, and there are 3 blue spheres. So if each particle represents 0.1 moles of a substance and the volume of the container is 1 liter, since we have 3 particles, that would be 3 times 0.1, which is 0.3 moles, divided by a volume of 1 liter, and it is equal of 0.3 molar. So the concentration of B is equal to 0.3 molar. So 0.3 ang gas B. For 8 concentrations, we have 1 particles, the 0.1 mole divided by 1 liter, which is 0.1 molar. So the concentration of A is 0.1 molar, and 0.3 divided by 0.1 is equal to 3. So, butang nato diri ang 0.1. Then, divide. It is equal to 3. So, QC at this moment, QC is equal to 3. Notice that we could have just counted our particles, that blues and one the particles that has 3 blues and 1 red, and said to be 3/1. So QC is equal to 3 and QC is equal to 3. So when QC is equal to QC, the reaction is at equilibrium. So next, we're gonna introduce a stress. So to our reaction at equilibrium, we're going to increase the concentration of A, which is kane. So here we're gonna add 4 particles of A to the reaction mixture of equilibrium. So the second particular diagram shows what the reaction looks like after we add those 3 red particles. So we started with 1 red particle and we added 4. So now there's a total of 5 red particles. As you can see in the second diagram, there are 5 particles, which is red, from the concentration of A. So 1, 2, 3, 4, 5. And then we still have the same 3 blue particles that we had in the first particular diagram. So let's calculate QC at this moment after we introduce the stress. Since there are 3 blue particles and 5 red particles, QC is equal to 3 divided by 5. So QC is equal to 3 divided by 5. And which is equal to 0.6. So since QC is less than QC is less than KC. So there are too many reactants and not enough products. So therefore, the net reaction is going to go to the right, and we're going to decrease in the amount of A, and we're gonna increase in the amount of B. So the third particular diagram shows what happens after the net reaction moves to the right. So we're gonna decrease the amount of A and increase the amount of B. So we're going from 3 blues in the second particular diagram to 6 blues in the third. And we're going from 5 reds to only 2 reds. Therefore, 3 reds must have turned into blues to get the third particle diagram to the right. And if we calculate QC for our third diagram, it will be equal to QC so 6 divided by 3 6 divided by 2, which is equal to 3. So at this moment, QC and QC, they're both equal to 3, so the equilibrium has been re-established. So it isn't always necessary to calculate Q values when doing Le Chatelier's principle, changing concentration problem. However, for its hypothetical reaction, it's useful to calculate Q values to understand that we're starting at equilibrium and then the stress is introduced, such as changing the concentration of a reaction or produced, and that means the reaction is no longer at equilibrium. So Le Chatelier's principle allows us to predict which direction the net reaction will go, or we could also use Q to predict the direction of the net reaction. So the net reaction will continue going in the new direction until Q is equal to K again. Now let's proceed into another possible stress, which is the temperature. So let's proceed into another possible stress, which is the temperature. So as an example, let's take a look at the hypothetical reaction where gas A turns into gas B. So delta H for this reaction is less than 0. So which tells us that this is an exothermic reaction. And for an exothermic reaction, heat is given off. Heat is released. So therefore, we can go ahead and write plus heat on the product side. So let's say that our hypothetical reaction is at equilibrium. And then we change the temperature. So we're going to increase the temperature. So according to Le Chatelier's principles, the net reaction is going to go in the direction that decreases the stress. And if we treat like a product and we've increased the temperature, it says that the amount of one of our products, and therefore the net reaction is going to shift to the left to decrease a product. So let's use the particular diagrams and the reaction quotient Q to explain what's going on when we increase the temperature in our reaction equilibrium. So we have here QC is equal to B divided by A, and then the first particular diagram shows the reaction at equilibrium. And let's prove that by calculating QC, we can get the expression for the reaction quotient QC by looking at the balance equation. So we have coefficients of 1 in front of A, and then 1 also for front of B. Therefore, QC is equal to the concentration of B to the first power divided by the concentration of A, and also to the first power. So to find the concentration of B, we know that B, so there are 3 spares, and if each spare represents 0.1 moles of a substance, so 3 times 0.1 is equal to 0.3 moles of B. So, and at the volume equal to 1.0 liter. So 0.3 divided by 1.0 moles, I mean 1.0 liters. So it is equal to 0.3 molar. So the concentration of B is equal to 0.3 molar. Then 0.3 divided by 0.3 is equal to 1. So QC at this moment of time is equal to 1. So Kc for this reaction is equal to 1 at 25 degrees Celsius. So Qc is equal to Kc. And when Qc is equal to Kc, the reaction is at equilibrium. So for this diagram, the reaction is at equilibrium. Then next, we introduce the stress to the reaction of equilibrium. So, and the stress is an increase in the temperature. So, in general, for an exothermic reaction, increasing the temperature lowers the level for the equilibrium constant. So, for this hypothetical reaction at 25 degrees Celsius, Kc is equal to 1. But since we've increased the temperature, the value for the equilibrium constant. So let's say it goes 0.5. If we increase the temperature to 2 degrees Celsius, so Kc is 0.5 at 30 degrees Celsius. So if we calculate Qc for our second particular diagram, which is Kane, we still have three blues and 3 reds. And the volume is still the same. Therefore, QC is still equal to 1, but the difference is QC has, KC has now changed. So QC is not equal to KC. So this diagram is not in equilibrium. And in this case, QC is greater than KC because QC is equal to 1 and KC is equal to 0.5. And when QC is greater than KC, there are too many products and not enough reactants. So when we say that this diagram is not in equilibrium, it is because one reactant or product is much greater than Kc. So it means that there are too many products and not enough reactants, and therefore the net reactions goes to the left. So when the reaction goes to the left, we're going to return into A. So we're solving. So we should see one piece turn into red. The red here is the A gas. So if we have 3 B and 4 reds, and 1 B turns into a red, which is a gas, and that gives only 2 blues and 4 reds. So now we calculate QC for our third particular diagram. So the concentration of B would be 0.2 molar and the concentration of A would be 0.4 molar. So QC is equal to 0.2 molar over the 0.4 molar. So divide 0.2 divided by 0.4, it is equal to 0.5. Well, Kc is also equal to 0.5, therefore Qc is equal to Kc. So, and the reaction is at equilibrium. And when a reaction is at equilibrium, Concentrations of reactions and products are constant. And finally, into our third stress, which is the pressure. The pressure of a system can be changed by it's either we're going to add or remove a reactant or product. Second, changing the volume of the reaction vessel. So it should be noted that adding an inert gas, which is one that does not take part in the reaction, has no effect on the equilibrium position. Then we have the Boyle's law, as it says that the pressure and volume are inversely proportional at constant temperature. Boyle's law can be written in the equation form P times B is equal to constant K. So changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure also will increase. So it should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So let's have an example here. So is what we call the Haber process, in which nitrogen and hydrogen react together to form ammonia. So we have 4 moles on the reactant side. So note nga mo na atong reactant side, then this is the product. We have 4 moles on the reactant side and 2 moles on the product side. So this means on the reactant side, we have more gaseous molecules, and on the product side, we have fewer gaseous molecules. So when the equation of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure, and when the position of equilibrium shifts towards which lower the pressure, so Kc doesn't change. So when the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left side because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side. So again, an increased pressure will shift to the equilibrium to the left, and the value of the Kc does not change. So what about if there are the same number of gaseous molecules in the reactants and products? So as you can see in this example, we have here the same amount of moles in each side, which is the reactant and the product. Two moles, and then on the product side we have also here 2 moles. So the position of the equilibrium will not change because they are the same number of gaseous molecules on both sides of the equation. So if we have equal number of gaseous molecules in the reactants and the products, changes in pressure have no effect on the pressure of the equilibrium. So summary, when we increase in pressure, the position will shift to side with fewer gaseous molecules. So value of Kc here is no change. So while we decrease in pressure, of course, it shifts to the side with more gaseous molecules. And again, the value of Kc, no change. Still no change. So when change in pressure with an equal number of gaseous molecules like pareha ani and the reactions and products. So change in equilibrium position, again no change. Same with the value of Kc, still no changes. And now we're done dealing with those stress. Now let's proceed and appreciate into the application of Le Chatelier's principle in real life. In industrial reactions, Le Chatelier's principle is used to optimize the yield and profitability of reversible reactions. So one example is the Haber process, which is used to produce ammonia from nitrogen and hydrogen gases. By manipulating the temperature, pressure, and reactant concentrations, the equilibrium position can be shifted to favor the formation of ammonia, increasing the yield and efficiency of the process. Second is environmental systems. So, in Le Chatelier's principle, in environmental systems, it can be applied to understand and predict the behavior of chemical reactions in environmental systems. So, for example, in the ocean, the equilibrium between dissolved carbon dioxide and bicarbonate ions is influenced by changes in temperature and pH. So when the ocean becomes more acidic due to increased carbon dioxide levels, the equilibrium shifts towards the formation of more bicarbonate ions, helping to buffer the pH and mitigate the effects of acidification. And third, biological systems. So Le Chatelier's principle is also relevant in biological systems. Many chemical reactions that occur in living organisms are regulated through this principle. For instance, the transport of oxygen by the blood follows Le Chatelier's principle. When oxygen levels decrease, the body responds by increasing the production of red blood cells and adjusting the oxygen carrying capacity of hemoglobin to maintain equilibrium. And lastly, the adjunct therapy for viral infections. Le Chatelier's principle has even been proposed as a basis for a new hypothesis to reduce the impact of viral infections, including coronaviruses. The hypothesis suggests that by applying the principle of Le Chatelier, the equilibrium position of the immune system can be shifted to better cope with the infection, potentially leading to improved patient outcomes. So these are just a few examples of how Le Chatelier's principle is applied in real-life scenarios. So by understanding and applying this principle, scientists and engineers can optimize processes and predict the behavior of chemical reactions and develop strategies to address various challenges in different fields.